Welcome back to Renewable and Sustainable Energy. This is Module 2, week number 4. The title of this module is Photovoltaic on Solar Thermal. I will start with solar cell and photovoltaic. Now, we'll talk about solar cell, photovoltaic systems, PV cost and efficiency. We will try to discuss the principles, parameters. Before I start, I would like to introduce the topic. And I start from history. We already see some animation and movies related to even 40-50 years back with solar cell and photovoltaic, and the expectation that it will take over the conventional energy sources and the technologies. And it's become reality, close to the reality. What happened today is we have large scale, large plants, not anymore only solar cell used to provide energy needed by satellite or small application calculator, but start to provide energy needed by cities or villages and cities, or more than this. Now, simply, photovoltaic is a device that converts light into direct electricity, DC. Okay, and when we put them together, we have what we call solar power to increase the power. We use different material. One of them, and well-known one, is the silicon. We will focus in this discussion on silicon because it is the most wide and let me use technology today everywhere in the world. And we can see here simple solar cell, as you can see here. This is in my lab. We will discuss, as I mentioned in this part, only photovoltaic. Concentrated solar power to be discussed later, but just this comparison, simple comparison, that the photovoltaic high performance, and today they use nanomaterial for coating and manufacturing it, and the technology get advanced with time, because we're talking about from 1954 into today, much improvement and progress in dealing with this technology. Comparing with the concentrated solar power, as you can see here, also low cost, high performance storage based on load market, and the advance in observer and reflector, and then fluid use. They use today nano fluid, and next generation is coming similar to the photo. Now, if I back to the history of photovoltaic, because some people still think that it's a new technology. No, it's not a new technology. The idea itself, photovoltaic, discovered by Becquerel in 1839. In 1870, he developed the first solid selenium PV with 2% efficiency. 1905, photovoltaic effect explained by Einstein. And in 1930, light meter for photograph common employed cell for copper or silicon selenium. Bell Lab developed the first crystalline silicon cell with 4% in 1954. 4 years later, they used it in Vanguard project to supply energy to the satellite. And in 1970, when the world energy crisis came, more interesting in this technology happened, and more investment and research developed. Also, first amorphous silicon cell developed in 1976. 1980, what happened is more, material have been used and efficiency been developed, and even it continue until 90 decade. But in 2000 decade, if I would like to summarize what happened there, I will say that smart become in buildings as a building integrated photovoltaic start to be part of the building, and regulation and policies are adopted by cities and countries, and also research and development continue with more investment in research. Prices get down, as we will talk about it later on. And solar electricity, we can see that large scale is there with hybrid systems. Sometimes they use it to with another technology, wind as example, or use it for electrolyzer water to produce hydrogen, and then use hydrogen and fuel cell to generate electricity for transportation and building. After 2010, I summarize what happened is a huge disseminate. I really don't know. It's difficult to summarize what's going on. Okay. Now, also, it's worth to mention, you will find many information in my recent book published related to photovoltaic thermal system in Springer Nature. And you can see here, this is in 2006. The yellow part here is represent the share of energy, global energy, let me say, profile. As you can see here, I try to classify it here into part for wind and solar biomass, for biofuel, for hydrogen, or more here in this bar chart you can see biofuel, bioenergy and hydro is higher than other, but this change, this percentage has been changed since that time, and it keep changing. The main countries in utilizing solar PV consumption is this is in mega ton oil equivalent, the energy is China, as we can see here, and European. They take over with respect to United States and India. And the efficiency, if we look to efficiency after 1980, it's become, let me say, sharp, going up. The efficiency improved clearly, and it reached around 40 plus minus percent. Still, this is in the lab, but we expect it will appear in the market in the next few years. Now, also here, the production, worldwide PV production between 1990 to 2009. This is all data, but just would like to highlight that. See, regardless the share, we know that China is always in the front, and on the level of manufacturing PV cell or utilizing it. But see, the growth is exponential. It's going up. It means this technology get interested by people and countries. Now, let me start with the principles of solar cell. I will start from the cell. We will discuss the cell, how we manufacture cell, what's happening inside the cell, what are the different type of cell, and the process. And then we model it. This is our discussion, this direction. This is the cell. Very simple. When I show you one in my lab, when we put them together here in series and parallel in one panel, we call it module. Okay, when we bring modules, put them parallel and series to increase the energy, also at the power, we call them array. So cell produce module produce array. Now this is the periodic table, and you can see here the white boxes represent the semiconductor. We classify the material based on their electrical conducting electrical current or electricity into insulator, which cannot conduct, example wood, or conductor, which is like example copper, conducting the current, or semiconductor in between. Now we will use semiconductor and we'll focus on silicon. You may ask, why silicon? Because it's the second material available in our nature, and most of our work today coming from silicon, okay, comparing with other material available here. Now, this is well-known graph available in internet, produced and updated almost yearly by NERA, National Renewable Energy Laboratory, which is a well-known lab in United States, and it shows the progress in efficiency. Okay, for different, these are different curves with different color to show different technology used to manufacture solar cell. But see here the efficiency approaching now 46. Okay. And gap above and above. Don't forget that we're only utilizing the visible part of the solar radiation spectrum. Okay. Now the silicon used to manufacture different type of solar technology. We have crystalline, we have amorphous. We will discuss them, but you can see I try to make a comparison here between crystalline, silicon, and amorphous. It's more pure here. You can see the shape here compared with non-uniform shape here. Now silicon have 4 electrons in outer band. Have 4 electrons. We will discuss how we make doping by using impurities to manufacture the solar cell. But before this, regarding crystalline silicon and amorphous, the amorphous, definitely we have crystalline and polycrystalline, or multi. Today they call it multi. They improve it. We see that the efficiency is in the range of 14 to 22. This is available in the market. Otherwise, it's higher in lab. The technology is well-established technology and stable. It's used, improved for long period of time. For disadvantage, until today, people still take cost of production. No, cost of production going down and down. Now we're talking about less than $1. Today is less than $1. Some of them $0.5. Okay, per watt, for solar cell per watt. And low absorbing coefficient is increased now, even if this is disadvantage, but it's increased now with the progress in, let me say, in the research. And large amount of highly purified feedstock use more material. Now they reduce it with the improvement in research. Amorphous, the advantages are high absorption. Its absorption because of the material is high. Established technology also, ease to integrate into building because it's flexible, as we'll explain later on. Excellent ecological balance sheet, so its impact on environment is explained, and less. Cheaper than the glass, metal, plastic deposit on it. It's very cheap material. Okay. Now disadvantage, its efficiency is low, and instability, it degrades in some cases. Okay. Now, before I go further, I would like to mention that the difference between flat plate and concentrator is, imagine this is my cell, okay? This is the normal cell. Now, the material I use here is, let me say, have a quantity number. I can reduce the material, but increase this. Definitely, this will reduce the use material, reduce the cost. But in another, from the other side, I would try to concentrate the light, increase the light observed by this cell by using lenses or mirrors. Okay, this is another way. Some people use the conventional, and some people they invest in lenses or mirror and reduce the material used for this. Definitely, this will create another problem, which is the heat, and we need to reduce by cooling. Now let's come to the how it works, the solar cell. Now, as I mentioned, we have insulator, conductor, and semiconductor material. The metal, which is the conductor, we can see on the atom level we have a valence band and conduction band in any material, and the gap between them is the energy gap. In the conduction band there is some electrons. Insulator, it's empty, as you can see here. But in semiconductor we can create small. There is a few, and we can create a few here electrons, and it will be close to conductor. Now, this gap here, electrons in the valence band, it needs energy to receive energy to jump into conduction band, so we create electrical current here. But this means that the energy observed by electron, it's enough to cross it to the energy gap. There is here a hidden, let me say, level which is called Fermi level. The electrons need to jump behind this, so it can be approaching the it's in the middle, it can approach the conduction band. Okay, now what happened with this semiconductor? We come to this semiconductor. This is the intrinsic, when there is no the pure, let me say, semiconductor. We try to use doping, put impurities. As example, for each million of silicon atom, we put one atom from some material. This will create either p-type, n-type, negative type, or p-type, positive type. In negative type, we create electrons in the conduction band, while in p-type we create holes in the p-type, in the valence band. Sorry. Now, the n-type, we use atom which have 5 electrons in the outer band, and it's called the donor because it's give extra electron, and this will use what we call it n-type. While the p-type, no, we have atom with the impurity is atom with 3 electrons, so there is missed electron here which create hole like hole. Example is for n-type, as you can see here, we will use phosphorus. Okay, you can see for silicon we have 4 electrons in the outer band, and if there is another silicon cell nearby, also it's connected with it in bond, make bond, and then with another atom and another atom. But when we put phosphor here, this electron connect to this electron with the cell, with the silicon atom, and this one with this one here, this one here. But we have extra electron because P have 5, not 4. So this electron will keep rotating on this network, coming from place to place. So we create movement of electrons, we create electrical current. Now in p-type, we use as example boron, B here. In boron we have only 3 electrons, so there is miss here, broken bond here. So what this one looking for electron to be filled. So if it is taken from here, another one created here, hole. It's like hole moving on the network, which is positive charge. Hole represented as a positive charge compared with electron, which is negative charge. Now when we bring this p and n type, this is n type and this is p type, we put them together. Okay, this is the n type, this is the p type. In p type the majority is positive charge, while in n type then majority carriers is negative charge. But when we put them as a sandwich, we create what we call a junction or depletion. This junction in the middle of depletion layer. Depletion layer, some electrons will jump this at the beginning, this junction, and some holes will jump to the other side. So this, until this happen at the beginning, until it reaches equilibrium, they create what we call depletion layer. Okay. Now we have p-type. The junction could be PN junction or PI internecine junction or Shockley barrier or heterojunction. I am going to explain them. PN junction is simply we put P and N, we create the junction here. P is higher level energy gap and N is lower level here, as you can see here. And when we put intrinsic in the middle between P and N, we change the characteristics, how it will perform. So electric field here increased. Okay. Now I explain this until okay. Now there is two operation mode here. Is the forward bias and reverse bias. Forward bias, when we reduce the barrier height. Okay, forward bias we reduce it. It was here. This is see how long it is from here to here. Now it's become here. We reduce it forward. We increase it in reverse bias. In forward bias, current will follow through the cell, while reverse bias, current will not follow through the cell. If we come to the characteristics, we will see that current density on the x-axis here, and voltage on the on the y-axis, and the x-axis will be the voltage. Now, usually for diode, which is also manufactured from silicon, this is the curve. But for solar cell, this is the curve. We need eliminated. Okay, we need light at the end. And how we can represent the current related to voltage for the cell? It's represented by one known equation, use Shockley equation, which is called Shockley based related to the scientist Shockley. Okay, the current I produced in the cell equal to the light generated current minus saturated current IO. Exponential Q is charge of electron, which is 1.6 10 to the power minus 19. V is the voltage across the cell. K is Boltzmann constant given here, is constant, and T is the temperature of the cell. Now, it's worth mentioning that when we have open circuit, okay, no current will follow in the cell. We have short circuit, no voltage across the cell. We can rewrite this equation here to rather than current in terms of voltage, voltage in terms of current. Also, it's worth mentioning that in short circuit and open circuit, no power will follow through to the load, but we can find the maximum power by multiplying them. V maximum, I maximum will be equal V open circuit I multiplied by fill factor, as you can see here for the cell. Now, the IV characteristics, they call it in this V, and there is PV, by the way, characteristic. IV characteristic, current here, voltage here on the x-axis, and the curve is this curve. This represents the characteristics of the cell. It means high current here with zero voltage, or high voltage here with zero current, and the maximum power approached in the middle here. Okay, definitely it's supposed to be in this way as a rectangular, but this part lose because of many effect resistances inside the cell, as I will explain later. Okay, for that we have here curve in this way. If we plot P with respect to V, this is the curve, and again this is the power maximum. Fill factor represent maximum voltage and current divided by open circuit voltage and multiplied by short circuit current. Don't forget, this is the spectrum, and the visible part is the part used to generate it. But how it gets generated? The process happens in this way. This light coming use the photon. Photon is carrying the energy of the light. When photon incidents coming on the valence band, it's give its energy to produce what we call exciton, electron hole pair, and some of the energy released as a heat, this is losses, and the electron get enough energy to jump through the gap. So if the energy is enough to approach the conduction band, crossing the Fermi level and then approaching then this means that we create active electron in the conduction band, which create electrical current. And when it reaches there, some energy also released because you don't need it, the electron here, so it's released. So we have losses here. For that, we expect the efficiency is low, and this is the situation. Now this is a direct process in the energy gap to produce electron. There is indirect one which use in a quantum of lattice vibration. It is not part of our discussion here. So only we discussed the direct here in this level. Now the solar cell, when we generate electrons, we need to collect them to take them to the outer, to the load connected to the cell. So what we have some bars, bus bar. This bus bar connected to fingers. These fingers, metal, it's collect the electron, generated electron. It's go to the bus bar, then we take it from the cell. And it's worth mentioning that we use what we call it anti-reflected coating. We coat the cell so to make sure that there is no reflection of the light from it and we lose. Okay. Now there is also what we call it heterojunction, and we can use here or tandem. Let me say tandem cell. We use different cells together. We put them, more than one cell, like a sandwich, to produce more power. And definitely the top one here have large band gap. The middle is mid band gap, and the lower one here at the end is a small band gap. This is also another technology. Now these cells, after we understand them, how we create the module and we create the array to produce energy for my light. What type of systems we use? We use three different type of system. One of them is the standalone. Standalone, it means we generate electricity from the PV cell and we give it to isolated load. As example, pump. Here we have pump. We give from the solar cell here